Welcome to lesson 4.3. This one is all about Riemann sums, and now we are going to continue to connect them with definite integrals. Feel free to pause this video at any point so you can take more notes. Otherwise, listen up, I guess. It's a little bit of a longer one. Feel free to, again, take some time with this. We will sort everything out once I'm back in school. All of these long summations are called Riemann sums. So everything that we've been doing so far, everything with your, summation f of ci delta x, all of those, trying to find the area of a bunch of different rectangles, they all fall under this category of Riemann sums. And so far, we've just been solving rectangles of the same width, right? They all had this width of delta x. But it is possible to have a Riemann sum with unequal widths. So we're going to talk about that a little bit. This is something I want you guys to be aware of. If you want, feel free to look up section 4.3 in your textbook to get a little bit more info. I'm taking some of these examples directly from the textbook, but they might explain it differently. So we're going to do this. It's not going to play a gigantic role, but I want you guys to be aware of Riemann sums and their different possibilities. So we're going to start with this example. We are going to consider this region bounded by this particular graph. So here's our function right here. They're showing us the graph of it right over there. And they're showing us a bunch of different rectangles, but you can see here the widths of all of these are quite different. So we know our A value is 0. We know our B value is 1. We're going to be using our normal limit summation thing. This is the Riemann sum that we are dealing with. But now, CI, instead of just being one of our endpoints, we're going to have to figure out how to construct a width with different intervals. All right, so they're telling us that CI is the right endpoint of the partition given by blah. So they are just telling us, hey, use this expression to represent an endpoint. But as you guys can see over here, all of our endpoints look a little bit different. You can kind of see how I have a 1 up top and then a 2 squared and then a bunch of dots and then this n minus 1 squared. So to create our definition for our width, and we're going to use this little I here because now I is going to be changing. I am going to have to plug I into my width. Previously, we've just been saying, hey, delta x is b minus a over n, and we would get an expression like, I don't know, a number over n, but no I. I wasn't plugging in any I value. Now, because we have different intervals, different widths, we're going to have to be plugging in, I'm kind of saying that with quotations, plugging in I'll put that down here, plugging in I to figure out the specific width for every single rectangle. All we're going to do is we're going to take our right endpoint, which they're telling us is I squared over n squared, and we're going to subtract it by the left endpoint of every single rectangle. We're going to notate that by using this I minus 1. So if I'm trying to find the width of my third rectangle, I would be plugging in 3 for I in both of these places. I would have 3 squared over n squared minus the previous endpoint, 2 squared over n squared. All right, so all we're doing is we're creating an expression that's going to help us figure out the width of every single rectangle. And to find that particular rectangle, I'm plugging in that number for I. So we're going to simplify this a little bit. We have I squared over n squared minus, I'm going to FOIL this out, I squared minus 2I plus 1 over n squared. We can combine some like terms over here. We have I squared minus I squared plus 2I. What I'm doing is I'm distributing this minus sign to all of these terms right now. Minus 1, and that's all over n squared. The I squareds cancel, leaving us with our variable width of 2I minus 1 over n squared. From here on out, everything is going to be treated the same. All right, so we're going to still be setting up our limit summation the same way we normally would. I'm going to have the limit as n goes to infinity of sigma from I equals 1 to n of f of ci, and they told us what that ci is. That's this. We're going to be using that times our now variable width. So let's go ahead and plug this all in. Limit as n approaches infinity, summation. I want to plug that ci into my original formula. Our original, function, not formula, was the square root. So I'm going to have the square root of I squared over n squared. That, again, is this value they told us to plug in. They had to give us that information. So this is representing the height of all of our rectangles times that variable width that we just came up with on the previous page. All right. Now you guys kind of know the drill from here on out. We want to simplify and we want to solve this summation. I'm going to take the square root of the top and bottom. So square root of I squared is just I, square root of n squared is just n. And then we have this 2i minus 1 over n squared. Let's go ahead and pull out the n's. Again, the dots are just representing the limit, just to remind us, hey, we're still taking limit. So I'm going to pull out a 1 over n cubed. I have n times n squared. That gives us n cubed. Summation of I times 2i minus 1. Let's go ahead and distribute that. So 2i squared minus I. And now I can split up those summations just a little bit more. I'm going to zoom in here. So I have 1 over n cubed, 2 sigma I squared minus sigma I. We're just going to keep on going. Let's use those formulas. I'm going to replace this all with n times n plus 1 times 2n plus 1. That's all over 6 minus the summation of I is just n times n plus 1 over 2. All right, and then again, we've talked about this in class. You guys can use whatever simplification methods you want as long as you're doing legal math. So for some of you, you might FOIL everything out. You might try to deal with the 6 and the 2 on the bottom here. Whatever is going to help you and make sense to you, you can do that method. I'm going to be foiling out this top piece right now. We've done this so many times, so I'm just going to kind of jump cut straight there. We have 2 outside here, and then we have 2n cubed plus 3n squared plus n. That's all over 6 minus over here. I'll distribute this n squared plus n over 2. All right, I want to do a little bit more distributing over here. I'll go ahead and distribute this 2 and be splitting up all of these into separate fractions. So we're going to have 4n cubed over 6, or 2n cubed over 3 plus 6. I'm multiplying this 2 right now with this term, 6n squared over 6, or just n squared. Then I'm taking this 2, I'm multiplying it over here, so 2n over 6 is just going to give us plus n over 3, minus n squared over 2. Remember to distribute that minus sign to both of these, minus n over 2. All right. At any point here, again, you got options. You can just keep going and you can say, hey, I'm going to distribute this 1 over n cubed. Or you could say, hey, I have some like terms. I want to combine them. You'd be dealing with some fractions. Up to you guys how you want to tackle that. I think I'm just going to distribute the 1 over n cubed, though, and go ahead and take our limit. So as I distribute that, I'm going to get just 2/3. Then I'm going to get plus 1 over n. Then I'll get plus 1 over 3n squared. Minus 1 over 2n, minus 1 over 2n squared. When you guys actually take the limit, all of these terms drop out. Again, think small over big. We're left with just 2/3. So the area under this curve with variable, I'll zoom back out, with variable widths, that area is just going to be equal to 2/3. Okay, so again, want you guys to be aware of this. This is not going to play a huge role in tons of problems you're doing, but it plays a role as we now connect Riemann sums to definite integrals. So that example used partitions having subintervals of unequal widths, right? We had to do that whole calculation to figure out a variable width where we were actually plugging in I. The reason this particular partition gave the proper area is that as n increases, so n is heading towards infinity, the width of the largest subinterval, and this almost seems counterintuitive, the width of the largest subinterval approaches 0. What that means for us is all of these rectangle widths, because I have so many rectangles, even the largest rectangle, even its width is heading towards 0, right? Again, think if I'm just in this interval from 0 to 1, but I have n approaching infinity number of rectangles, that's crazy. Then yeah, the width of even that largest one is approaching 0. And again, this is going to be a key feature in developing our definition for definite integrals. In 4.1, we talked about indefinite integrals. Now we're going to make this connection with definite integrals. I'm going to show you this on the next slide. Again, I want you guys to have experience with the mathy language in your textbook. I don't need you to read something like this and be like, oh yes, understood immediately. But I want you to have some exposure to it, all right? So this is saying, let our function be defined on a closed interval. So honestly, that's pretty generalized. They're not giving us too many conditions here. I have a function, it's on an interval from a to b. We're going to use some different notation here. We're going to let this little delta be a partition of a given by this over here. So they're basically just saying, hey, in between a and b, you have all of these possible x values. You have an infinite number of x values in between the start of your interval and the close of your interval. Your width then is always going to be one endpoint minus the previous one. So it could be x2 minus x1. It could be x100 minus x99. That's all they're saying over here. Every single width is just going to be one x value minus the one right before it. And you could plug in any number for I. If ci then is any point in the ith interval, then the sum, okay, this is exactly what we were just using in the previous example, right? C is any point. They gave us that point in our first example. I'm using this variable width, and C is somewhere in between these two x values. That's called the Riemann sum for this particular partition. I'm going to keep on going with this. Again, pause this video as you need to. Just trying to introduce you guys to some of these new notations. The width of the largest subinterval of partition delta is called the norm, and it's denoted with this notation over here. So here we're saying if every subinterval is of equal width, then we just define this normally, this way we've been doing the past couple of days. I can say, okay, the norm is just equal to delta x, and we know that delta x is b minus a over n, right? These are your endpoints up here. This is the number of subintervals down here. So that's just what we know. Okay, so that's if I'm dealing with subintervals of equal widths, or each rectangle has an equal width, then cool, my norm is what it's always been. But for a general partition, so that could maybe mean I have unequal widths, then I'm going to use a slightly different definition. I'm going to say b minus a over the norm is going to be less than or equal to n. It's just a slightly different definition. Again, I don't want us to get too stuck in the weeds here. They're just saying, hey, we're trying to generalize this right now. You guys have been used to this definition for width. The width is going to be the same for all of your rectangles. Now we're saying, hey, I can generalize that. I can broaden that a little bit. I'm just going to use a different thing. I'm going to use this norm. And that norm is pretty similar. It's b minus a over something, but it's a little bit different. Okay, again, don't get stuck in the weeds. I'm introducing this right now. I'm going to keep on going. The next slide will give us a little bit more detail. So, as the number of subintervals approaches infinity, so n is heading towards infinity, then your norm approaches 0. So, as your norm approaches 0, n approaches infinity. That's what we've been saying these past couple slides. Even if I'm dealing with rectangles of different widths, because the number of rectangles is getting so large, even the width of the largest rectangle is still heading towards 0. The converse of this is not true. That's what they're saying down here. They're just giving you an example of an interval going from 0 to 1. As n approaches infinity does not necessarily imply that the norm heads towards 0. It has to be in this order up here. As the norm heads towards 0, then I know that n is approaching infinity. For this particular example, our largest subinterval is just 1/2. So they're saying, hey, if n is approaching infinity, it doesn't necessarily mean the norm is always heading towards 0, but this starred one up here is true. Folks, that's plenty with Riemann sums. We're going to move on to definite integrals. You'll see on the next slide why we had to talk about the norm a little bit. It's in the definition of a definite integral. So our definition for definite integrals, it looks very similar to what we've been dealing with, except instead of n goes to infinity, they're saying the norm is going to 0. So again, they're just generalizing it. If you're seeing this symbol for norm, it just means, hey, maybe I don't have equal widths anymore. But secretly, I'm going to tell you guys, a lot of the times we're still going to be dealing with equal widths. They're just trying to generalize. So all of that previous discussion is just saying, hey, instead of n going to infinity, I'm saying the norm is going to 0. I might have intervals of different widths. That is all. So if this limit exists, then f is said to be integrable on that particular interval. And I can rewrite this entire thing, this limit summation, as our definite integral over here. In one of the videos that I had in the Wednesday subplans, it talks about how dx, you can think of it as just teensy tiny increments of x. So that's almost like the counterpart for width. It's almost the counterpart for delta x. Your summation symbol, it's kind of the counterpart for this part, adding up a ton of little tiny rectangle areas. All right. A is called your lower limit. That's always your lower number. B is called your upper limit. That's your upper number. And we're going to see how right now definite integrals are different than indefinite integrals than what you guys learned about in section 4.1, but they're related. They're different but related. So we've seen the symbol before, right? You guys have seen this integration symbol. An indefinite integral, what you guys learned in section 4.1 is a family of functions. So you guys learned that method, but then you always had to add c to the end of everything. A definite integral, on the other hand, is always just going to give you a number. It's giving you a very specific result. It's giving you a number. So indefinite integrals, what you did in section 4.1, it was always giving you a family of possible functions that could satisfy the integral. Definite integral is always going to just give you a number. And then this theorem down here, I mean, you can just jot this down. If you know that something is continuous, you know that you are able to take the integral of it. You can do that in real shorthand. Just say continuity implies integrability. All right, so all we know what to do right now is translate from a definite integral into a Riemann sum. When I get back, we will talk about easier method. Haha, it's coming. But we have to do all this background work to have a really good appreciation for what's going on behind the scenes here. You guys did a problem like this in the Wednesday subplans. So we're translating this. This 2x is the function that they're giving us. The -2 and the 1, that is the interval that they are giving us. So if I want to say that this is equal to a Riemann sum, we're going to have to piece some things together here. The function is still just going to be, f of ci. I need to figure out what a good ci is going to be. I need to figure out what our width is going to be. Delta x, and for this one again, we're just going to go back to equal intervals. That's going to be our best bet for this. So b minus a over n, or 1 minus -2 over n, that gives us a width of 3 over n. ci, we're going to still just do what we've been doing for that one, a plus delta xi, -2 plus 3i over n. All right, so let's go ahead and plug that in. We're going to have the limit as n approaches infinity for the summation from I equals 1 to n of our function was 2 times x, so 2 times -2 plus 3i over n. That whole thing representing heights times the width of every single rectangle. I'm not going to solve out this whole one. You guys did some problems like this yesterday. I trust that you guys now have a lot of experience solving these summations. I'll tell you the answer for this one. By the time you do the whole limit, you end up getting -3 for this. So if you want to pause and do that for some extra practice, feel free. But otherwise, once you have it set up like this, you're solving it the way that we've been solving. All right. I know this is a long video. We're going to keep going a little bit further. It says 22 slides. I don't think we're going to do all 22. We'll see. Because the definite integral in example 1 is negative, it does not represent the exact area. Okay, so we didn't work this whole one out, but I told you guys, hey, you're getting an answer of negative. A negative area doesn't make tons of sense, but this is what the graph would look like. So you can see I have area under the curve here, but then I have area kind of above the curve over here, all right? So I can treat any area that is under my x-axis, that's going to come out to give you a negative number. When you sum this small positive area with this larger negative, it's going to give you a net negative. So that means definite integrals can be positive, they can be negative, or what if you have the same amount of area above the x-axis as below? They could also just be 0. All right, so definite integral as area, again, it's not necessarily representing exact area, but if I know that my section is all above the x-axis, then it most definitely is representing the area, all right? So if it's continuous and non-negative, that's the huge thing here. If I know it's non-negative, then yes, my definite integral is representing area. If you know that you're dipping below your x-axis, then I can't say it's exactly representing area. Again, we have to kind of make this weird approximation thinking about negative area. So if it's non-negative and continuous, then area represents your definite integral over here. And I'm going to show you guys a couple of shortcuts for a couple different types of definite integrals. So for instance, if you have something like this, well, if my function was just a number, think through what kind of graph that would be. That would just be like a horizontal line, right? So I would just have this horizontal line. That's my function of 4, and I'm evaluating this from 1 to 3. Well, then the area under that curve, that's just going to be a rectangle, right? So to figure out the area over there, all I really need to do is say, well, the height is 4 and the width over there is 2. So my area, anytime you just see a number inside here, you're just calculating rectangle area. Height times width, 4 times 2 gives us 8. All right, so whenever you guys see a number, think rectangle, find your height, find your width, calculate your area. You'll have some homework problems like this. If you ever see a line, something like x plus something, x minus something, then you're dealing with a trapezoid. So this first one, it's just going to look like a rectangle. That's the area that you're trying to solve for. Anything that falls into this category is going to give you a trapezoid. I'm going to give you a little hint here. Your area of a trapezoid, maybe you remember this from geometry, maybe you don't, is 1/2 base 1 plus base 2 times your height. Again, if you think about this graphically, x plus 2, okay, I'm starting up here. Here's my y-intercept. Here's my line over there. And I'm looking at this from x equals 0 to x equals 3. And I'm trying to find the area under this. Well, the bases of a trapezoid are always the parallel sides. So base 1 is going to be 2. To figure out what base 2 is, I would need to take 3 over here. And I would need to plug it into our function. Our function is just x plus 2. So that means that this base must be 5. This base must be 2. Our height over here is going to be 3. So be careful with the rectangles versus the trapezoids. Be careful with your bases and with your heights. Make sure that the two vertical lines are your bases. So to find my area over here, I'm going to have 1/2 base 1 is 2. Base 2 is 5. That's going to be multiplied by 3. 1/2 of 7 times 3 gives us 21 over 2. So again, use these geometric shortcuts. If you just see a number, it's a rectangle. If you see this, it's a trapezoid. If you see anything that looks like this, it's a semicircle. So your graph for this one, I'll draw this out. If you can think back to the circle equation, which is x squared plus y squared equals r squared, they have basically just rearranged to solve for y over here, which means this 4 term must represent our r squared. So our radius must be 2 for this circle. And if you're like, what the heck is she talking about with semicircles and trapezoids? This is just, calling us back to good old geometry days. You guys have dealt with these equations before. I can guarantee it. It might have just been a little while. So this is your refresher on geometry. To find the area of this circle, well, we know our general area of a circle equation is pi r squared. Here I'm dealing with half of that. we said that our radius was 2, and you can kind of figure out your radius from your upper and lower boundaries, or again, you can say this 4 is your r squared term. So I'm going to get 1/2 pi r squared, or just 2 pi, and that's your area. All right, so in your homework, you might see some problems like this. Use your geometric shortcuts. All right, folks, we are going to stop there. We have a little bit more. We will finish this up on Monday whenever I get back. Thanks for powering through this video.